Okay, so today we are going to discuss about the protein purification technique. Okay, so the first part is the preparation of sample for protein purification. Okay, so as you all know, that majority time we purify intercellular protein. Okay, so the proteins are inside the bacterial cell or plant cell or animal cell. So you have to disrupt the cell and extract the protein from that cell envelope, from inside the cell envelope. Okay, and then you have to prepare the sample with proper buffer and all other different conditions so that protein stays stable and functional throughout our purification like workflow. Okay, so for that, first we are going to discuss little bit about what is protein and how, like, what are the force that stabilize protein structure, and how we can prepare a protein sample in such a way that it would be, like, stable in the solution. Okay, so as you all know, proteins are polymer of amino acid. So amino acid, these are small biological compound that has a amino group and a acid group. Okay, and a R group. That R group determine what kind of amino acid it is. There are 20 different amino acid. They varies each other due to their, like, R group, isn't it? So based on the R group, the chemical property of the R group, there are some amino acid which are aliphatic amino acid, some are aromatic amino acid. Some R group has positive charge, some R group has negative charge. And as protein, it's a polymer of amino acid. So based on the composition of their amino acid, protein might have different properties. Okay, so based on the composition, so if the protein has more and more positively charged residue amino acid, then the protein might show a different kind of characteristic compared to another protein that has more and more negatively charged amino acid, or sometimes it has more and more aromatic amino acids. So all those things, it changes the property of the protein, or how this protein going to behave in solution. Okay, if it has more hydrophobic residues, so then it will be less stable in solution. If it has more hydrophilic residue, then it will be way soluble in solution. So depending on the composition of the amino acid, protein, the different property of protein in solution varies. Okay, so one of the characteristics of amino acid is, you all know, is called isoelectric point. So what is isoelectric point? Isoelectric point is a pH at which the net charge of the protein would be 0. Okay, so it would have equal amount of positive charge and equal amount of negative charge. So similarly, just like a amino acid, the protein itself also has a pI. So at that pH, the net charge of the protein would be 0. So if the charge of the protein is 0, then there would be more interaction between protein molecule to protein molecule, and there is more possibility that the protein molecule may get aggregated, okay, and get precipitated from the solution. So we have to make sure that we don't keep the protein in its pI. So whenever we are going to prepare the solution, prepare the sample for protein purification, we have to have a idea about what is the pI of the protein, so that we keep the protein in a solution. The pI would be little bit away from, like, the pH of the solution would be away from the pI. If we keep it the protein in pI, then protein might get aggregate and precipitate. Okay, so as we said, like, it's a protein is a polymer of amino acid, and it forms peptide bond between two amino acid, one amino group and another carboxylic group, and a water get removed and peptide bond forms. And that particular polymer, initially we have, this is the primary structure of the protein. Okay, so defined amino acid, they are linked to each other by peptide bond. Okay, so that linear structure then fold itself with different stages of folding, and then it end up with a folded form. The folded form is active. The unfolded form of the protein is not active. Okay, so our aim is to purify protein mostly in folded form. Even if we have to use a condition where protein might get denatured, okay, then we have to then again renature the protein. So that's they call, like, we sometimes we purify protein in denaturing condition. So there the protein might get denatured. Then to get a functional protein, we have to refold it. But that's a different thing. And in normal scenario, we try to keep native condition. Native condition means a condition that is as close as possible to the living cell. Okay, so that protein don't get denatured. And after the purification, we get a folded protein. So the primary structure of the protein get folded into secondary structure like alpha helix, beta sheet, and then finally those alpha helix and beta sheet, they rearrange themselves and make a tertiary structure. Okay, so tertiary structure, majority time tertiary structure is the folded form of the protein, and that's the functional stage of the protein. Okay, so once more than two polypeptide, more than one polypeptide, they fold together and form quaternary structure. Like, hemoglobin, it has four polypeptide chain, and it's a tetramer. So our aim is to purify protein in its tertiary or quaternary structure. Okay, because these are the biologically active structure. So now we want to discuss what are the forces that stabilizes these quaternary and tertiary structures. Okay, so as you can see here in the picture, so one of the, like, uh, most useful interaction that stabilizes the three-dimensional structure of protein is hydrophobic interaction. So what is hydrophobic interaction? This is the interaction between two hydrophobic residue. So why they interact to each other? Because those residue, they have phobia for water. Okay, so they always, in a water solution, what they will do, they will always try to enter inside the protein interior. Okay, that is the force that bring all those residue close together. Okay, and that's how in solution, in water solution, protein get folded. Okay, so it's the hydrophobic interaction that is the most, like, preliminary driving force for protein folding. Okay, so the hydrophobic residues, they have phobia, they don't like water. So what they do, they will fold inside the interior of the protein, and that's how they come together and they interact to each other. And other than hydrophobic interaction, there is one of the most stable interaction is called disulfide bond. Okay, so this is a only one example of covalent bond that stabilize protein three-dimensional structure. Okay, so it's formed between two cysteine residue. Okay, so once it get oxidized, it form SS disulfide bond. Okay, so this is the one of the most stable interaction that can hold the three-dimensional, or when means three-dimensional structure of the protein together. And that's why you will find, like, the protein which are really stable, like heat stable protein. Okay, they have, like, way more disulfide bond than compared to normal, like, regular protein. Okay, so it gives stability to the protein, and because disulfide bond is very hard to break, even temperature cannot break disulfide bond. Okay, that's why most of the heat stable protein, they have multiple disulfide bond. Okay, other than disulfide bond and hydrophobic interaction, there are ionic interaction. Ionic interaction is between two residue of opposite charge. Okay, so they interact each other by Coulombic interaction, and it stabilizes the protein. And one of the most abundant interaction in tertiary structure of protein is hydrogen bonding. So hydrogen bonding is between any functional group which has OH, and that's in OH, that's the hydrogen donor, and acceptor is either O or N. Okay, so hydrogen bonding is really abundant in three-dimensional structure of protein. Okay, so you see, other than this disulfide bond, rest of the all the bonds, they are non-covalent interaction. Okay, so they are weak in nature. So even little bit of heat or even room temperature can break all those non-covalent interaction, and that's why a folded protein can get unfolded because of little bit of temperature. So our aim is to keep the protein folded and functional throughout our purification step. Okay, so then we have to know what are the factors that can denature protein, so that we can avoid those conditions during our protein purification. Okay, so here is a list of factors that can destabilize the tertiary structure of a protein. Okay, so one of the factor is temperature. As we already mentioned, like the non-covalent interaction is the major interaction that stabilizes the tertiary structure. So they are very weak, and they can break in even in with little bit of temperature increase. Okay, so we have to avoid exposing our protein to any kind of temperature shock until and unless the protein is a heat stable protein. Okay, so that's why from preparation of sample to the end of the purification, we are going to keep 4-degree temperature, or we'll keep it the protein or sample in on ice. Okay, so that they stay stable. Okay, so if it is a protein sample, we should avoid multiple cycle of freeze and thaw. Okay, so if we keep freezing and thawing the protein, then it denature the protein because of, like, ice formation and all other different, like, reason. So tearing force because of mechanical shaking or something, that can also, or vortexing, that can also denature protein, because like we should avoid, like, vigorously shaking the protein sample. And so that's why we should put the sample in a particular condition what mimics the physiological condition, means natural pH, ionic strength, and everything. Okay, and sometimes, like, dilution effect, these conditions have very uh, insignificant effect, but still they are important. Okay, other than all these things, oxidizing, like, environment. Okay, so inside the cell it's kind of reducing. Okay, so when we bring the protein out of the cell, so in our like, uh, this oxygen air environment, in our air we have oxygen, so it might oxidize the protein. And once the protein get oxidized, what happens? One of the most stable bond, that is disulfide bond, it get, like, the disulfide bond will get breakdown. Okay, so that would destabilize the protein structure. So that's why we would add reducing agent in our preparation, sample preparation. If we cannot, like, avoid exposing it to air, what we can do, we can chemically make the solution reducing, so then it will be, like, effective to, like, keep the protein in reduced form. So that's why we normally add dithiothiotol or beta mercaptoethanol, these two agent that are reducing agent. So protein also get denatured because of the heavy metal. Okay, so heavy metal has two effects. First, there are so many metalloproteases are there in cell extraction. Okay, so to inhibit those metalloproteases, we had to add EDTA. So EDTA is a chelating agent that chelate all the metal, and it will not be available for the metalloproteases to bind and act on. Okay. So to inhibit metalloproteases, we have to add EDTA, and other than that, sometimes heavy metals, they can interfere with the interaction between amino acids and other thing, and then that's how it can denature the protein. Okay. So another thing, we have to make sure there is no microbial growth. Okay. So if microbes are growing in our protein sample, what it will do? It will use the protein as nutrient source. For that, what it will do? It will secrete some proteases, and it will chop down the protein into small pieces, and then it will be easier for the bacteria to uh, engulf those protein, or uh, take those protein as a nutrient source. So we have to make sure there is no bacteria growing or microbes growing. So for that, we lot of time in between our purification step, what we do, we pass the protein solution through 0.22 micron filter. Okay. So we do filter sterilization. We cannot do like heat sterilization or anything else, because it will denature the protein. So a lot of time what we do filter sterilization. We pass it through 0.22 micron filter. And another thing that is also important, to make sure that there is no protease, because protease would chop down our protein. So to avoid the degradation of protein because of protease contamination, we add protease inhibitors. Like EDTA is one of the inhibitors that I already mentioned that can inhibit metalloproteases. So there are other protease inhibitors we'll discuss later, like PMSA, aprotinine, leopeptine, and pepstatin. These protease inhibitors that we use in our sample preparation, so that all the serine and threonine proteases, they get inhibited and don't degrade our protein of interest. Okay, so in the protein purification step, we have different steps. Okay, so the first step would be the preparation of sample. Okay, so preparation of the sample, so that we do with the uh, breaking of the cell envelope and extracting the protein from inside the cell to the buffer solution. Okay, next step is isolation or capture. Okay, then we do some intermediate purification, and finally we do polishing step. Okay, so we are going to go step by step to all those purification process. So for beginning, we are going to discuss today the extraction of protein, or the sample preparation for protein purification. Okay, so for protein purification, for extraction of the protein from inside the cell, we have to disrupt the cell envelope. Then only the protein would be extracted into the buffer of our interest. So for that, we can use different process. Okay, some are mechanical process, some are non-mechanical or chemical process. Okay, so among the mechanical process, the shearing force is one of the highly used technique. So bead mill and ultrasonic sound or high pressure homogenization, these are the techniques that we normally use for cell disruption. For non-mechanical process, we do majority time enzyme lysis or detergent lysis, because acid or alkali can also lyse cell, but that also bad for stability of the protein. So we don't want to, you see, we already discussed, like we don't want to change the pH to a very extreme low or very extreme high, so that protein would get denatured. So acid and alkali lysis we normally do for DNA extraction, but not for protein extraction. For protein, we will do either enzyme or detergent, like very uh, polite detergent, which is not harsh for the protein structure. So let's discuss one by one some of the cell disruption techniques. Okay, so one of the mechanical method is bead mill. So this is nothing but a drum with metal balls. Okay, and when we rotate the drum, those metal ball, they crash the cell, and disrupt the cell membrane or cell wall, and that's how it extract the protein that's entrapped inside the cell wall or cell membrane. Okay, so you see there are shearing force that is acting, impact, and uh, hitting force. So these are the force that act on the cell wall or cell membrane when the bed meal is rolling. So this is one of the technique that is most used because this is very useful for large scale process. So whenever we are talking about protein purification, we have to think about the industrial application also. So in industry, when they need to extract protein from huge few 100 kilo of sample, so then using laboratory techniques is very difficult or scale up. So that's why they use this kind of mechanical technique that gives good result and is easy to scale up. So ultrasonic sonication, this is for laboratory scale. So what happens? So we use ultrasound vibration of 15 to 20 kilohertz, and that create a shearing force in water, okay, in solution, and that can rupture the cell membrane and extract the protein from the cell envelope. Okay, but two limitation of this technique is, first of all, you cannot uh, scale up this technique. Okay, this is for laboratory scale. Okay, it cannot be continuous method. And second thing, while sonication, it generate huge amount of heat, so you have to keep the sample in very ice cold condition so that the heat get dissipated. Other than that, the heating would denature the protein sample. Okay, so there is another thing is called French press or high pressure homogenizer. So in this technique, what they do, with high pressure, we send the cell through a small capillary or orifice. Okay, so in the beginning of that capillary, it faces a huge amount of force. Through the capillary, it faces the shearing force, and once the capillary ends, so because of the sudden release of the pressure, there is cavitation. Okay, so because of all these forces, cell wall and cell membrane get easily disrupted. So this is one of the technique that is also can be scale up, and this is one of the useful technique and most efficient technique that is used for cell disruption. Okay, so other than this mechanical process, what we can do chemical lysis using either detergent or enzymes. Okay, so detergents, like in the membranes, they are made up of lipid bilayer, and detergent, they are zwitterionic molecule, so they can disrupt the structure of the membrane, and once the structure gets disrupted, the membrane break down and it release all the content inside the cell membrane. So normally we use HDS, but HDS is an anionic and strong detergent, so it can denature, it will denature the protein. So if we are trying to purify protein in denaturing condition, then we can use this one. Other than that, we have to use mild detergent like non-ionic detergent like Tritonex, NP40, Twin 20, all this mild detergent. So we can also lyse cell using enzymatic lysis. So the name of lysozyme that degrade bacterial cell. So it degrade the peptide or glycan layer. So if we are using a gram positive bacteria for protein purification, then lysozyme is good enough to break down the cell wall and then cell membrane. Okay, but for gram negative bacteria, it has a thick cell wall on top of peptide glycan. So we have to use a combination of, majority time we use a combination of either detergent and the enzyme. So pro and cons of different methods. So mechanical, this is not selective, non-toxic also. Okay, and a majority time these are very suitable for large scale. Okay, and this is fast technique, and although this is energy, it can consume a lot of energy to run the bed meal or like a bed meal or like the ultrasonic sonicator or the pressure high pressure instrument. Compared to that, the chemical and enzymatic method. So chemicals are a lot of time toxic, and they are not good for the protein also sometimes, and it's not that efficient in large scale. Okay, so same for enzyme also, but for enzyme is like the advantage of enzyme is it is selective compared to rest of other technique. So it selectively degrade the cell wall and cell membrane, and is less toxic and also not harmful for the protein structure. So in general, what is the buffer composition that we normally use for cell lysis? So we'll go for a buffer, either trisacchyl or phosphate buffer, depending on the uh, our necessity, and the pH would be 7.5 to 8.5 in general. If it is a if we need like a special pH, then we can change it. It's not like this is a rule of thumb, like we can go for almost neutral to little bit of basic pH. Okay, then we normally add 300 to 500 millimolar sodium chloride. So sodium chloride, this is salt that would stabilize on and keep the protein soluble. Okay. Other than that, if we don't add any salt, then it might get aggregated and precipitate. So this is kind of salting in. Okay. For that we use a little bit of salt, but adding salt is optional. Then we can add glycerol. If the protein is highly hydrophobic, then adding glycerol. Glycerol is also a molecule that has both hydrophilic and a hydrophobic part. Okay, so it stabilizes very hydrophobic proteins. EDTA that we already mentioned, like it's a protease inhibitor, as well as it remove all the divalent ion, so that or heavy metal ion, so that it can stabilize the protein. Again, DDT or beta ME. So these are the reducing agent that keep the environment reducing, so that the disulfide bond don't get oxidized and break down. Okay, but depending on the column that we're going to use, so DTT is not good for if we are using nickel NTA column. So for that we have to think about adding reducing agent. And then finally, protease inhibitor. We should definitely add some protease inhibitor like PMSF or aprotein, leopeptin, pepstatin. These are the protein or peptide molecules that inhibit different kind of proteases. Okay, so that our protein don't get degraded because of the cellular proteases. So at the end, well, I'll suggest to read and go through this review article that discuss macro scale and micro scale cell lysis method. Okay, so uh, that's all.